Welcome to lesson 100 in your HL level IB math course. So before this lesson, you should have read page 573 to 576 in your textbook. And you should have some idea of what this list of key terms mean. Let's begin by talking about some vector basics. So when we measure quantities, we can classify quantities that have a size only, like magnitude only. We call those scalar measurements or scalar quantities, something like distance of 50 kilometers. When we have quantities that can be described using a magnitude and direction, say like I'm traveling at 100 kilometers per hour east, or I'm moving 100 meters east or 2 levels up. These are called vector quantities, okay? To represent vectors, we can use diagrams that look like arrows. They're directed line segments that have an initial point, which we call the tail, going from here to a terminal point, and we represent that using a head with the arrow sign, okay, or with the arrow symbol. Algebraically, we can also represent vectors using ordered pairs or ordered triples. In IB, in your textbook, we can also write vectors using what we call a column vector. AB or A, B, C, okay? Vector symbols, they have, usually you'll see that is a letter with an arrow going above it, or two letters indicating the endpoints, A, B, right? And then with a vector symbol over it, or in some textbooks, they just boldface and italicize the letters. The magnitude or the size of vectors are represented by, something that looks like an absolute value symbol. And we basically say that a vector is defined by how large its size and also the direction. So the position of a free vector in space is not fixed unless we're talking about something called a position vector, which has a reference point, okay? Two vectors are equivalent if and only if they have the same magnitude and direction. You can also say this in the opposite way, which is if two vectors have the same magnitude and direction, then they are equivalent, okay? And pay attention to your drawings if you're showing vectors using diagrams. Even though if you're not using, we're not measuring exactly with a projector or ruler, you should still represent vectors using like a relative size. The longer the vector is, the larger the magnitude will be associated with that quantity. So let's start by looking at positions and displacement. Using the diagram here, I have 5 points A, B, C, D, which forms a rectangle, and point E, which we're given the information that the length going from C to D is the same as the length going from D to E. So the first thing that we're going to talk about is going from A to B. So I can show that using, this program is not the best, but here we can show that with an arrow, which is a vector, AB. This is called a displacement vector. Which shows a change in direction. Okay. And then next, what about going from A to B to C? Then I have AB already. Let's go to B and C. And I can represent this path. The most direct way to connect my starting point and the end point is using another vector, AC, right there, okay? As such, I can say that the vector AC, which is the resultant of putting vector AB and vector BC together, one after another, okay? So we say that AC, we call this the resultant. of a vector addition. And when we do vector addition, we have a head to tail connection on the diagram right here. I should use arrows. Okay. And then how about going from A to B and then back to A? Well, that means I will have to go take AB and then come back. I'm still doing head to tail, but the second vector is now called B, from B to A, right? And it results in no change in position. So I can represent that using a 0 vector. If we look at this in a different way, I can also say that the vector AB is the negative, of the vector BA. So these are opposite vectors. With the same magnitude, but a different or opposite direction. Cannot spell. Okay. So next, part B. Let's compare the displacement from C to C and C to D and then C to E. Well, C to D is right here. C to E is all the way there, but we also was told that DE has the same distance as CD. So what I can say is that the vector CD is the same as the vector DE, right? Same direction, same magnitude. And look, the vector CE is CD plus DE, or now I can say that this is CD plus CD, or simply 2CD. This is called a scalar multiple. Okay. So what is a scalar multiple? Well, it changes the magnitude of a vector, but it does not change the direction. Okay, it only affects the magnitude. Part C. Now we have vector AB, we call it vector P. We have vector AD, which we call vector R. Midpoint, all these things. Okay, so let's represent CM using P and or R. Obviously, the vector CM is half the length of AB and in the opposite direction of AB. So I can say that this is negative 1/2 vector P. How about vector CE? Vector CE is twice of vector CD. And vector CD on the diagram, we can tell is is the opposite of P. So this is negative 2P. DB is, so let me get rid of this. DB goes like that. So it closes a triangle surrounded by vector P and R. Because we started from point D, we must be thinking in this direction, which is opposite from vector R. So this is negative R, and then head to tail connecting P. Or we can say that this is P minus R. Okay? On the previous page, we already looked at what vector addition is. So let's take a look at what happens here. So on this diagram, we have vector P, vector Q. If I want to show vector P plus vector Q, I actually have to reproduce vector Q so that instead of looking the two vectors being connected tail to tail, which is not, an addition of vectors, right? I will actually show a head to tail connection for addition. And here is vector Q, which means that I started from here, I ended up here. So the blue vector shows P plus Q. Is this equivalent to Q plus P? Well, let's see. So now we're going to start from vector Q, which is at the bottom right here. And then I have to add vector P, so I reproduce vector P so that I have a head-to-tail connection. And of course, when I close up that triangle, I still have P plus Q being the same. So we say that vector addition is commutative. Example 3. Given the vectors A, B, C, sketch A plus B plus C using the triangle law of addition. What we're trying to achieve here is to show that, well, when I do the head-to-tail connection, I can only work on two vectors at the same time. So is the resultant of A plus B, which is this guy here, and then plus vector C, so 3 down to the left, the same as adding A to the resultant of B plus C. So we'll show that using this method. So here's the left side, okay? Now, so let's show the right side and compare whether, it matters which two vectors I add first. So vector B for this way plus vector C, 3 down to the left. This is B plus C. Let's add A to it. So don't forget, A has to connect to the tail of B plus C, right? And then when I close this up, it's a horizontal vector that goes 1, 2, 3, 4, 5 boxes to the right. How does that compare to my first results? I think they're the same, right? So we have proven using a diagram the associative law of vector addition. And then in example 4, let's try to illustrate the result of A minus A. When we subtract vectors, we actually say that we're adding the negative vector, okay? Well, vector A goes to the right and up. Vector negative A goes down to the left, spanning the exact same length, meaning the result is a 0 vector. So 0 vector has undefined direction and a 0 magnitude, okay? What if we compare A minus B versus B minus A in vector subtraction? So let's see. A minus B means A plus negative B. Vector negative B goes to the right 5 steps, which gives me this resultant. What about B minus A? So vector B goes 5 to the left. Vector A, well, negative A would be 2 left and 4 up. 1, 2, 3, 4. Okay. And then B minus A would be, oops, it's not the greatest. This one here. So points up to the left. Compared to two blue vectors, you should notice that they have the same length, but pointing in opposite directions. In other words, that's what we need to make the equality true, okay, in the red box. Here's more vectors. Express the following in terms of A, B, C. Taking a look at the diagram, I have vector FE, AF, BE, and AG, FD. FE is parallel to AB, but it goes in the opposite direction as vector A. So that's what it is, okay? So follow the same, idea that we have talked about. I'll give you 30 seconds to work out the next 4 questions. Okay, so what do you think? AF. For me to go from A to F, I can follow the path of A plus C, because BF is the same as AE. For BE, go from B to A first and then A to E. That means it's negative A plus C or C minus A. AG, I'm going to take AB, then BC, then CG, which really is A plus B plus C. You can have this in any order you want. What about FD? FD, I can go F to B, so negative C, B to A, negative A, and then A to D, positive B. So B minus A minus C in any order that you want, okay? Example 7. 2 vectors AB make an angle of 30 degrees with each other. Magnitude of A is 3, magnitude of B is 5. Calculate magnitude of A plus B. So here, magnitude of A is 3. The angle between 2 vectors is always measured between their tails. So this is 30 degrees. Magnitude of B is 5. And then I want A plus B. Well, it looks like I need to redraw the diagram somewhat to show vector addition with a head to tail connection. And the resultant, A plus B, is the vector that I need to calculate the magnitude, okay? Using parallel lines theorem and co-interior angles, I also know that the angle opposite from my unknown side is 150 degrees, right? 150 plus 30 has to be 180. I can use cosine law. So A plus B squared, 3 squared plus 5 squared minus 2, 3, 5. Cosine 150. 9 plus 25, 34. 10 times 3, 30. Cosine 150 is related to cos 30, root 3 over 2. In the second quadrant, negative root 3 over 2. Okay? You still need your calculator because you need to take the square root of the right side to find the length of A plus B. So round it to 3 significant figures, it's 60.0. So on the last page, let's sum up what we have talked about scalar multiples. So scalar multiples of vectors change the magnitude. It may change the direction, but it's limited to either keeping the same direction as your original vector if the k, the scalar multiple, is greater than 0, is positive, But if k is a negative number, real number, then it will turn the direction 180 degrees, opposite. Ka is parallel to or collinear with vector A. And this is a very important property that we will be referring to later on in the subsequent lessons. So let's draw. Given vector v on the diagram, 2v, well, 2 is positive, and so I'm going to expect 1v, 2v, a longer vector in the same direction as v. The vector negative v, same length, opposite direction. Negative half v, half the length or half the magnitude, opposite direction. And we can form new vectors using any 2 or 3 or 4, basic vectors, and adding them together or adding their scalar multiples together, okay? And this is called linear combination of vectors. So if I have vectors v and u, what does the vector 2v plus 3u look like? Well, 2v, 1v, 2v, plus or head to tail, 1u, 2u, 3u's. And here is my new vector 2v plus 3u. What about negative a third of u minus v? This is the same as saying negative 1/3 u plus negative v. So I'm going to do this. Negative a third, so going to the left, just 1 unit. And then negative v means instead of going left and down, I go up and to the right. And it's 1, it's the same thing. So here. Okay. And then this is the results. That's it.